Today's lecture is on PID controller for 2 input to output system. The control of 2 input to output processes is difficult than the SISO processes, mainly due to the interactions between the loops. 2 input to output systems are from the family of multi input, multi output systems. Many methods have been proposed earlier in the literature for the design of controllers for 2 input to output processes. Attempt will be made in this lecture to design simple PID-P controller, a 4 parameter controller for the 2 input to output system. Now, we have got uses of such processes in various real time systems in power plants, aircraft, chemical industries and in many other fields. The uses of such processes are very common nowadays in real time scenario. What a 2 input to output processes look like? The process is denoted by 4 subsystems given as G11S, G12S, G21S, G22S. So, a 2 input to output process can be represented in this form. Now, the control of the 2 input to output system can be accomplished with the help of a PID controller in the feed forward path. For the first loop, a PID controller in the feed forward path for the second loop. We have inserted proportional controllers in the inner feedback path. So, KB1 is the proportional controller in the first loop and KB2 is the proportional controller in the second loop. This PID-P control is a 4 parameter control for the TITO system. One can have PI in the feed forward path and PD in the feedback path as well. That case will not be discussed in today's lecture. We shall concentrate on the design of a PID-P controller rather in this lecture. For each in analysis, one can represent this PID-P controller scheme in some convenient form. First, we shall assume a specified form of the PID controllers. Let the PID controller be represented in the transfer function form as given over here. This is a parallel PID controller. So, depending on various values of I, for all I equal to 1 to 2, we shall have 2 controllers for the TITO system. So, the 2 controllers would be GC1S and GC2S. These are the feed forward path controllers. Now, we know earlier that for a SISO system, when a PID controller is present in the feed forward path, a PID controller, then we have a single input, single output process. For that case, if we have some inner feedback proportional controller, let us say P1, then the same structure can be reduced to some convenient form for each in analysis and design of the controllers. Now, let me redraw the block diagram that will appear as PID plus P1 in the feed forward path with the single input, single output process G, and now a pre-filter is to be added and that pre-filter will be given by PID upon PID plus P1, and we shall have the reference input over here. So, a single input single output process with a inner feedback controller P1 and a PID controller in the feedback path can equivalently be represented in the single input single output control scheme, where the PID plus P1 will be in the feed forward path with a pre-filter in the reference path, and the pre-filter dynamics will be given by PID upon PID plus P1. Using this equivalence, now it is possible to convert the TITO system into some simpler form as shown over here. Now, GS represents the 2 input 2 output process, which is now subjected to a new PID controller, where the controller PID, the parallel PID controller is added with the proportional controller KB1, and for the second loop the new PID controller has got the proportional controller KB2. Now, the scheme has got also pre-filters given by the upper one as GCL1S upon GCL1S plus KB1, and the bottom one pre-filter is given as GCL2S upon GCL2S plus KB2. This scheme enables us to design the new PID controller. After designing the new PID controller, the parameters of the pre-filters can be set for controlling the TITO system. Now, effort will be made now to design the new PID controller. Let us assume the new PID controller, which is now available in the form of a series PID controller, be given by GCLIS star is equal to GCLIS plus KBI. Please note that KBI, the proportional controllers are added, thus giving us the new PID controller. GCLIS represents the parallel PID controller, whereas the KBI are nothing but the proportional controllers. Now, the form of the new PID controller is given over here, which is a series PID controller with proportional gain KCI star and derivative time constant TDI star and integral time constant TII star. So, for all values of I 1 to 2, we shall get 2 new PID controllers for the 2 input 2 output process. Let the plant dynamics be assumed to be available in the form of GMS is equal to GM1S 0 0 GM2S. That means, the plant dynamics is represented by the diagonal transfer matrix GMS, where GMIS is given as the elements of the transfer matrix are given by GMIS, which is equal to Ki times e to the power minus dis upon TIS plus 1 square. The plant dynamics is assumed to have repeated poles at minus 1 upon Ti. So, we have got repeated poles for the plant dynamics. The TITO process can be identified in this transfer matrix form. Only when the TI/TO process dynamics is available in this transfer matrix form, we shall be able to make use of the design process we are going to discuss later on for the design of controllers for the TI/TO process. As we know, this represents the time delays associated with the process dynamics. So, di gives us d1 and d2, where d1 is the time delay associated with the GM1s and d2 is the time delay associated with the dynamics GM2s, and T1 and T2 are the repeated poles or the time constants of the upper loop and the lower loop of the TI/TO process. Now, after assuming that the dynamics of the TI/TO process is available in this diagonal matrix form, one needs to also define the dynamics of the controllers, new controllers available in the diagonal transfer matrix form. Now, GCLI star S is having elements GCN1 CL1S star and GCL2S star. GCL1 star S is nothing but KC1 star times 1 plus S T D1 star times 1 plus 1 upon S T I1 star. Similarly, we can find or write the expression for GC2 star as H KC2 star 1 upon 1 plus S T D2 star times 1 plus 1 upon S T I2 star. So, the form of the new PID controllers are written over here. With these forms of the new PID controllers, we shall now try to estimate the parameters of the controllers using phase and gain margin criteria. For that, for each in analysis, let us assume that T D I star is equal to T I. With that assumption, the loop transfer function becomes G M I G C L I star j omega is equal to K I K C I star e to the power minus j omega d I upon j omega t I plus 1 times 1 plus 1 upon j omega t I star. So, the frequency domain representation of the loop transfer function is given in this form. Then applying the gain criteria, it is possible to write expressions like the magnitude of the loop gain is equal to 1 and the magnitude of the loop gain at the phase crossover frequency is equal to inverse of the gain margin. Now, omega g I in this expression represents the gain crossover frequencies. Similarly, omega p I in the second expression is for the phase crossover frequencies. So, with the gain and phase crossover frequencies, it is possible to write the two equations related to gain of the loop. So, loop transfer function gives us the two expressions as shown over here. Now, the magnitude of the loop transfer function can be further written in the form of k I k c I star upon omega t I square plus 1 root it times 1 plus omega t I star square root upon omega t I star. So, this gives the loop gain in absolute form. So, the loop gain in absolute form can be represented in this form, but when we make use of the first expression, this expression further can be written in the form of k I k c I star is equal to omega g I t I star root of omega g I square t I square plus 1 upon omega g I square t I star square plus 1. So, it is very easy to get this expression from this condition. Similarly, the second expression can be simplified and written in the form of a m I k c I star is equal to omega p I t I star root of omega p I square t I square plus 1 upon omega p I square t I star square plus 1. Next, we shall make some assumptions for each in designing controllers for the TITO process. What are those assumptions? One can easily assume omega g I t I to be large compared to 1. So, when omega g I t I is greater than 1, that gives us the numerator as omega g I t I only. Similarly, when omega g I t I star is very large compared to 1, then the denominator of the square root becomes omega g I t I star. Then this expression has got numerator and denominator like this, which can further be written in the form of k I k c I star is equal to omega g I t I because of the cancellation of the terms. Similarly, with the assumption of omega p I t I to be very large and omega p I t I star is greater than 1, this assumption when made in this expression results in the simpler expression given as a m I k c I star is equal to omega p I t I. Now, these values of gain and phase crossover frequencies can always be set with proper choices of the controller parameters. Since we have been trying to design the parameters, therefore, these choices are valid. Now, with these choices of gain and phase crossover frequencies, it is always possible to get simpler equations like this from the gain criteria. So, the two gain criteria here will be used later on to estimate to find simpler expressions for the unknown parameters of the new PID controllers. Now, the phase criteria can be written as at the phase crossover frequency omega pi, when the point lies on the negative real axis, the phase crossover frequency gives us an expression like pi plus argument of gmi gcli star j omega pi is equal to 0. So, this is the loop gain in frequency domain. So, angle of the loop gain at phase crossover frequency plus pi must be equal to 0, because the phase crossover frequency points refers to a point on the negative real axis where the angle is minus pi. Similarly, the phase margin conditions gives us an expression pi plus argument of the loop argument angle of the loop at gain crossover frequency omega gi is equal to phase margins. So, omega gi is the gain crossover frequencies and phi mi represent the phase margins of the loops. So, with the help of the assumption for the inverse tan function, tan inverse as x is equal to pi x upon 4 when x is less than 1, and when tan inverse x is equal to pi upon 2 minus pi upon 4 x for x is very large than 1 is made use of in the phase criteria. Obviously, one can get the simplified expressions like pi upon 2 plus tan inverse omega gi T I star minus tan inverse omega gi T I minus d I omega gi is equal to phase margin. Now, one can substitute the tan inverse function over here, which will result in an expression of this form. So, tan inverse functions are substituted, which results in the expressions pi upon 2 minus pi upon 4 omega gi T I star plus pi upon 4 omega gi T I minus d I omega gi equal to phi m I. Where are we trying to substitute the tan inverse function? Because it is very difficult to solve this nonlinear equation. So, unless one makes use of this assumption, it is very difficult to solve this nonlinear equation. Similarly, for the second nonlinear equation, with the use of this assumption, the nonlinear equation is obtained in the form of a linear one, not exactly a linear function, rather I can say the nonlinear function involving tan inverse has been simplified to a very simpler form, which gives us pi upon 2 minus pi upon 4 omega pi T I star plus pi upon 4 omega pi T I minus d I omega pi is equal to 0. So, the two equations we get from the phase criteria with the help of the arctan function, tan inverse function, give us these two equations. Earlier we have got two equations for the gain criteria. Using the gain criteria, we have obtained two simpler equations, which are shown over here. So, making use of the four equations now, four unknowns can be estimated. What are those four unknowns now? For us, the unknowns are omega gi, omega pi, and we have got the unknowns K C I star K C I star and T I star. So, these are the 4 unknowns, all others are knowns in the 4 equations. What are known in the equations? The time delays d i's are known. So, let us separate out the known and unknown parameters. So, known parameters are d I, t I and a m I, the gain margins and the phase margins phi m I. What are the unknowns? Unknowns are omega g I, omega p I, the crossover frequencies and the proportional gain K C I star and the integral time constants T I star. So, with the 4 equations, 4 unknowns can be evaluated. Instead of solving a set of nonlinear equations to evaluate the or to estimate the 4 unknowns, with little manipulation it is possible to find explicit expressions for the unknowns, and those explicit expressions are obtained as K C I star is equal to C 1 upon K I, T I upon D I, T I star is equal to T I upon 1 plus C 2 times T I upon D I, and already we know that T D I star is equal to T I. This is the assumption we made at the beginning. So, with this assumption we proceeded and we have been able to find explicit expressions for the 2 unknowns of the new PID controllers K C I star and T I star. Now, in the expressions C 1 is equal to 2 phi m I plus pi times a m I minus 1 upon 2 times a m I square minus 1, and C 2 is equal to 2 a m I C 1 times 1 minus 2 a m I C 1 upon pi. So, these are the 2 constants used in the expressions, explicit expressions for the unknown parameters of the controllers. Now, what are known and unknown in this case? Let us see again. C 1 and C 2 are known to us. User defines, so when user defines the phase and gain margins, phase and gain margins given as phi m I and a m I. So, these are known now, because user has to define these phase and gain margins. Then C 1 and C 2 constants are known, C 1 known, K I known, T I known, D I known. So, that way these explicit expressions will enable us to estimate the unknowns of the new PID controllers, which are available in the series form. Thus, the PID controllers parameters are estimated. Now, we have seen that our TITO systems are subjected to a proportional controller KB1 for the first loop and another proportional controller KB2 for the second loop. So, these are the 2 proportional controllers employed in controlling the TITO system. Similarly, we have got the feed forward path PID controllers with parameters KC1, TI1 and TD1 for the first loop and Kc2, Ti2 and Td2 as the parameters of the PID controller for the second loop. So, how to calculate back these parameters? Actually, our TITO process employs controllers with these parameters only. So, one needs to calculate back the parameters of the parallel PID controllers employed for controlling the TITO process. For that, using simple calculations, one can find out these relations. Now, the parallel PID controller parameters KCI, TDI and TII can be obtained from the parameters of the new PID controllers with these expressions, using these expressions. Now, let us not go to the last part. How are we getting these expressions? With each one can find out these relations, starting with the new PID controller expression, which is given as GCLI star S, is defined as GCLI S plus KBI, which is equal to KCI times 1 plus 1 upon TIIS plus TDIS plus KBI. So, let us simplify this expression, which gives us KCI plus KBI. The two proportional controllers are clubbed together and the remaining parts can be given as KCI upon TIIS plus KCI TDIS. But we have seen that GCLI star S is also given as KCI star times 1 plus 1 upon TII star S times 1 plus TDI star S. Now, this is the form of the new PID controller, which upon expansion gives us KCI star times 1 plus TDI star upon TII star plus KCI star upon TII star S plus KCI star TDI star S. So, one can compare this with the final form for the new PID controller. So, upon comparison, it is not difficult to get KCI plus KBI is equal to KCI star times 1 plus TDI star by TII star, which again can give us the relation KCI is equal to KCI star times 1 plus TDI star by TII star minus KBI. So, this is what exactly we have obtained earlier. The relation shown over here, the first relation gives us the expression which is Kci is equal to Kci star times 1 plus Tdi star upon Tii star minus Kbi. That is how we obtain the same relation. So, using other terms upon comparison, we have to see that this term must be equal to this term, because we are comparing the dynamics of the transfer function form of the new controller with that of the parallel PID controller with that of the parallel PID controller and the additional proportional controller in the inner feedback path. So, obviously, comparison of this term with this term gives us Kci upon Tii is equal to Kci star by Tii star, which again can be written as Tii is equal to 1 upon Tii star times Kci, no, this Tii will go to numerator. So, Tii is equal to Tii star times Kci by Kci star. Now, using this expression, the upper one, using this expression now, I can write down Tii as Tii star times Kci divided by Kci star will give us 1 plus Tdi star upon Tii star minus Kbi upon Kci star. So, this is what we have got earlier also. If you look at minutely, then in that case the Tii is equal to Tii star time 1 plus Tdi star upon Tii star minus Kbi upon Kci star, and we have also obtained the exactly same relations from the analysis. Tii is equal to Tii star 1 plus Tdi star upon Tii star minus Kbi upon Kci star. Similarly, comparing further the remaining terms of the two realizations, it is not difficult to obtain further the relations for the relations between the parameters derivative time constant parameter of the two controllers H. H we have seen here this Kci Tdi star. So, Kci Tdi is equal to Kci star Tdi star, which again gives us Tdi is equal to Tdi star times. Now, we will have Kci star upon Kci, which is same as Tdi star times 1 upon 1 plus Tdi star upon Tii star minus Kbi upon Kci star. So, these relations helps us to calculate back the parameters of the original PID controllers that we had employed in the TITO control scheme. These are the original PID controller parameters which are calculated from the parameters obtained from the new controllers. So, new controller parameters, are KCI star, TII star and TDI star. But we know that TDI star is same as TI, whereas the original controller parameters are original controller parameters are KCI, TDI and TII. So, using these relations, we calculate back the parameters of the original PID controllers along with the parameters of the two proportional controllers for both the loops. Now, what one can observe from these relations that KBI should be less than this term, otherwise what will happen? KCI will be negative. When KCI will be negative, similarly TDI also will be negative and TII will also be negative. So, all these constants will be negative or unrealizable, which is not allowed in closed loop control systems. Will assume negative values unless the first term is greater than the second term. So, this factor is very important. So, design of KBI depends on the values for TDI star, TII star and KCI star. So, although we might have got design values for KCI star, TII star and TDI star, those might not be acceptable to us unless this condition is satisfied, unless this relation holds, unless KCI, TDI and TII are positive. They must be positive. So, KBI is generally designed heuristically. After designing the values for the new control parameters, new controller parameters, then only the values for KBI are chosen. Next, using the same relation, I can say KBI is equal to epsilon times KCI star. Now, epsilon has to be less than 1 and that guarantees that all the parameters of the PID controllers will be positive. So, simply designing the parameters of the new controllers may not ensure desired control of the TITO system. In that case, one must ensure this condition to get all the positive values, all the parameters to be positive. That means, all the parameters of the new as well as the original PID controllers to be positive. This condition must hold. Again, for simplicity in design, generally one chooses KB1 is equal to KB2. So, with this choice, it is easy to design all the parameters of the controllers employed in the TITO system. Next, we shall go to the simulation study. Let us consider a TITO process dynamics given by this transfer function matrix GS, which has got 4 elements and each 4 elements are nothing but the first order plus date time representations. So, we have got enough interactions in the TITO system. The 2 loops of the TITO systems have got significant interactions. Now, the dynamics of the TITO process with the help of proper identification procedures may be obtained in this form. So, the model transfer function matrix for the TITO process is obtained in the diagonal form, where the diagonal elements are given as 32.273 e to the power minus 0.2042 s upon 1.269 s plus 1 square, and the second diagonal element is 8.178 e to the power minus 0.2667 s upon 0.578 s plus 1 square. Off diagonal elements are assumed to be 0. Next, choosing the gain margin of 4 and phase margin of 30 degree for the first loop and gain margin of 3 and phase margin of 45 degree for the second loop, controller has been designed. Initially, we get the design values for KC1 star, KC2 star, next TI1 star, TI2 star, and subsequently TD1 star and TD2 star. Then using the relations just now we had discussed, using these relations, the controller parameters of the original controllers are obtained as this and this. Of course, with the choice of KB1 is equal to 0.2 and KB2 is equal to 0.2. As we have said, KB1 is equal to KB2 enables us for each in design. Then with the controllers in the loops, the performances of the TITO system are obtained as shown over here. The first loop has got a set point change, unit set point change at time t equal to 0 hour, and the second loop has got a unit set point change at time t equal to 20 hours. Then the responses of the two loops are shown over here. The upper loop response is given here and the second loop is giving a time response of this form. The responses shows us acceptable settling time, overshoot and speed of responses. So, we have got quite satisfactory overall responses, improved performances from the PID-P scheme. So, splitting the P control helps us in obtaining satisfactory performance of the TITO system. In summary, we can say that the TITO controller has proportional controllers in the inner feedback paths, and the proportional controllers have got significant roles in improving the performance of the TITO system. Now, not only the inner feedback proportional controllers help in improving the performances, rather they help in reducing the loop interactions and the stability of the TITO processes. The controller parameters are also designed for the SISO models of the TITO process for some specified loop phase and gain margins. Basically, the design technique available for SISO models have been employed to design controllers for the TITO process, and simulation results of course show us improved performances with respect to overshoot, settling time and speed of responses. Although comparison has not been given, often it is found that the PID-P controller results in satisfactory performances compared to PID controllers alone in the loops. Now, certain points to ponder on this TITO system control are: the first point could be how are the loop interactions or stability improved by the inner feedback controllers. Inner feedback controllers enable us to place the poles of the loops at some desired locations. So, placing the poles of the loops at some desired locations helps us not only in designing perfect controllers for the system, rather that helps also in loop interactions. Obviously, the controllers play a role when the poles of the loops are placed at some desired locations, the loop interactions automatically get reduced, and stability of course can always be improved with the help of providing inner loop controllers or inner controllers in both the loops. Now, second point is how to choose KBI. Now, as you have seen, this KBI has to be less than KCI star. So, first obtain the design values for KC1 and KC2, and based on that, using the condition that KBI is a function of epsilon times KCI star and epsilon is less than 1. Using that condition, the KBI values are chosen. Next point is it necessary to choose KB1 is equal to KB2 for designing controllers for the TITO system. When we design PID-P controllers for TITO system, often it has been found from extensive simulations that the choice of KB1 is equal to KB2 results in improved performances of the loops, but suitable choices of KB1 and KB2 also can lead to significant reduction in loop interactions and stability of the closed loops. That is all in this lecture.